Good morning. So, today we will continue with the same topic, that is thermionic energy materials and devices. In the last class, what we discussed was what is the basic electron emission process. After giving some historical perspective of electron emission phenomena, we have seen that there are three primary processes, rather four processes by which electron emission can take place. So, one process which was started long back and now this is the topic of our discussion, that is thermionic electron emission. Second is photo assisted electron emission. Third is field emission of electrons, and fourth is secondary electron emission. So, out of this we have seen how this thermionic emission can take place when we heat a material, and what is the basic configuration when we try to understand the thermionic process in a thermionic generator. We have to have an emitter which is to be heated, and when this heated emitter emit electron, those electrons are collected in another electrode, that is collector, which is in a low temperature or room temperature condition, and then when this electron flows back through the outer circuit, it generates power if any load is connected across that circuit. So, this is a typical phenomena of thermionic emission and the thermionic energy converter. And then we discussed that what are the requirements of a good emission, and we have seen certain properties of the material which are essential for a better thermionic emitter. In fact, today we will discuss in detail about different materials. So, one property which is the most important for a thermionic emitter material is the work function. This is what we have discussed, and work function is basically the energy required to emit or for emission of electron through the surface or crossing the surface binding energy to the vacuum. Okay. And if the work function of the material is less, the emission is better. Okay. Apart from that, also there are some other important properties of material which decide a good thermionic emission process. And then we discussed about efficiency of a thermionic generator, how one can calculate the efficiency and what are the factors those decide the efficiency of a thermionic converter or thermionic generator. And then we discussed specifically one important thing, that is space charge effect in a thermionic generator, which are basically the electron flow from emitter to collector. It may happen that there are some electrons which are located surrounding this emitter material, creating a space charge and then hindering the flow of further electrons towards the collector. And therefore, how this space charge effect actually change the energies. We also discussed about the phenomena in terms of energy levels, defining Fermi energy, vacuum energy, work function, etc. And that also gives us an idea that the voltage whatever is generated in a thermionic generator is basically difference between the work function of the emitter and the collector. Okay, so let us just look at what are the key components of a thermionic converter. So, we have already discussed, let me just again elaborate these key components of a thermionic converter. So, we know that the emission takes place in an emitter which is a cathode of the thermionic converter, and there are certain properties which actually decide this emission process as we have discussed and we will discuss further. And the second part of thermionic converter is anode or collector, okay, which is at lower temperature, and the function of this electrode is to collect electrons efficiently. Third is interelectrode gap. This is a very important thing which I mentioned in the previous lecture. This interelectrode gap actually decides the overall performance of the thermionic generator, or it is one of the important parameter which decide the performance of the thermionic generator, and it has to be optimized. Then of course, heat source. There are several heat source which we talked about. There are some natural heat source, one can have artificial heat source also, okay. And also we have seen that when such devices are used in satellite, one can use a radioactive material as a heat source, okay. So there are several heat source. Nuclear power plant also generate lot of heat, so this can be used as a heat source, and then the solar power also can be used as a heat source, okay. So heat source is one of the key component of a thermionic converter. And then the output circuit, electrical output circuit, this is also a part of the thermionic generator, because in order to generate the energy, the electron has to flow back, okay, and it crosses across a load which is there in the electrical circuit, and this is the way it delivers power to the circuit or to the load. Now, we look at the thermionic generator or thermionic converter from the perspective of what are the components that contribute to heat in this particular device or in this particular configuration. So, we know that basically there are two important things, one is emitter and another is collector. Okay. So, the role of emitter is when it is heated, the electrons are emitted from the emitter, and the role of collector is the electrons which are emitted from the emitter gets collected in the collector. Okay. So, now let us see how many components of heat are contributing to this entire configuration. We can think about this heat is nothing but some heat energy which we are supplying to the emitter, and this energy is carried away by the electrons, and then the heat energy or heat output energy from the collector, which is rejected in a sink. But there are many other components also which are connected in this entire thermionic generator or converter. So, therefore, we have to look into different components of heat in the thermionic generator. Okay. So, Q in is what we can say that heat input, okay, or the input heat, which is actually is from a source, heat source, it is coming to the emitter material, or this energy, heat energy is absorbed by the emitter material, and then it is emitting electrons. So, you can see these dotted lines and these green spots, they are electrons, and the dotted line is something that the heat which are carried by the electrons, and we can define as Q therm. Okay. So, now they are going to the collector. Okay. Now, we have different path of heating also. Different paths means one path is that heat is actually carried by the electrons which are emitted from the emitter. But there may be some internal support from emitter to collector, but they are not floating, they must be supported by something, and if they are supported by something, then there is a heat flow through those support also. Okay. So, let us call it Q conduction, this is the second part. All right. So, now we know that in thermionic generator, I already told you that there are space charges, okay, and space charge is a very difficult situation, and it is very difficult to get rid of this space charge. In order to neutralize this space charge, people use cesium vapor, okay. So, in between these two electrode, and they are actually being purposefully they have been added to this chamber, because so that they become a sort of positive ion, and eventually they actually attract electron, neutralize those space charge electrons. But as they are there, or if we put this cesium vapor inside this thermionic generator, then there is another path of heat, that is through the vapor. So, we have another path, okay, that is called Q vapor. Now, another important quantity is through the radiation, Q radiation. So, what is Q radiation? Q radiation means again if we look at the emitter here, and then the electrons are emitted from the emitter and carrying the energy, but there is always a possibility of radiation that we cannot avoid. Okay. So, this radiation or this energy or Q radiation, this will also come to the collector. Okay. So, this is also a positive term of heat. Apart from that, so there are some lead, etc. Okay. So, we can have a heat component of lead, that is wire which are getting heated and can be added to this component. Now, another thing is whatever connecting wires etc. are there in the circuit or in the entire thermionic converter device, there is always a possibility of heat loss. Joule heating we cannot avoid. As soon as a current flows, there is a Joule heating. So, this is a negative contribution. Okay. So, all these quantities of heat actually contribute to this entire thermoelectric conversion process, okay, or in this thermoelectric energy generator. All right. Finally, we have Q out, which is the output heat, from the collector and then gets rejected to the sink. Okay. So, we understand what are the components and what are the contributions of different heat energy in the thermionic generator. Now, I will just make a brief comparison between thermoelectric generator and thermoionic generator. We have already discussed about TEG in detail and TEG devices. So, there also we used to have the temperature difference, one hot junction, one cold junction, and when we have two junctions or they are at different temperature, there is a potential or EMF generated across the junction. So, there is a way it produces energy, but here in thermoionic generator there is definitely a hot emitter and a cold collector, but the energy is generated as I mentioned that when electron flows from emitter to collector, collector collects electron and it gives back this electron through the circuit, there is an electrical energy generation. Okay. So, this is a basic difference between a thermoelectric generator and thermionic generator or thermionic converter. So, if you look at again that how this TEG device was, there is a hot side here which we used to call the heat source, and then we used to have two semiconductors. One is P type semiconductor, another is N type semiconductor, and there is a cold side. Okay. So, this is the flow of charge, electron flows in this direction when we create a temperature difference between the hot and cold, eventually giving a potential here. Okay. This is the structure of a TEG device, a simple TEG device, and the TIC or thermoionic converter. So, this is again hot side. Okay. So, this is actually an emitter and the electron is going to cold side and then it is flowing in this direction, generating a potential and coming back here. Okay. So, these are the two device configuration. So, now let me look at what are the technical parameters, what are the difference of TEG and TIC in terms of some technical parameters. So, let me first see this temperature range in degree centigrade. So, generally we have seen this TEG, the temperature is not beyond 1000. In fact, you do not want to operate at very high temperature, but depending upon which material you use, you can increase the temperature difference. Okay. But what we have seen in case of TEG, if you increase the temperature difference, then there is an increase in efficiency. Okay. But selecting a material for a very high temperature is sometimes difficult for TEG, but therefore, the range is maximum you can consider that up to 1000. Okay. In case of TIC, the temperature range is high, because we can use material with different melting point, and there are some materials whose melting point is very high. And if we increase the the temperature, then we can have a better emission. Okay. So, we need a material which has lower work function and high melting point, so that we can have a good emission at higher temperature, at very high temperature. In fact, that is what is the main function of a TIC. Okay. When we talk about the material, we have seen there are different materials which are used at thermoelectric generator. Conventionally, we used Bi2Te3, that semiconducting material, silicon germanium. So, Bi2Te3 works at relatively lower temperature, okay, and SiG works at relatively higher temperature that we have seen. All right. There are some other materials of thermoelectric generator which work at intermediate temperature, various temperatures. Okay. For TIC, the emitter material is, there are several emitter materials, I will come to different emitter materials, but one very popular emitter material is refractory metal like tungsten. It is chosen in such a way that it has relatively lower work function and it has high melting point. As I mentioned, that these are two most important criteria before we select a emitter material of a thermoionic converter. Okay. So, now what is the electron transport mechanism? It is drift diffusion, and here thermionic electron emission, which we have already discussed. Type of thermal losses, thermal conduction, and here it is thermal radiation. Along with that, definitely there is a Joule heating, all right, which we have discussed. When we look at experimental efficiency, so far TEG devices have not shown a very high efficiency. Although lot of materials have been developed, a lot of materials have been assembled up to nanomaterial, quantum well and so on and so forth. But when we come to a practical device, the efficiency is not very high, 2% or maybe slightly higher. Okay. But here we can have a higher efficiency. Okay. These are typical number. Okay. One has to see the technical chart of different devices, okay, that are being used, but these are typical number, and here we can see the efficiency is higher as compared to TEG. You remember that when we discussed TEG and both TIC, we just compared it with an engine, Carnot engine, which just work on the principle of temperature difference of hot junction and cold junction. Therefore, efficiency depends on temperature difference of hot junction and cold junction. Okay. So, if we can have a high difference in temperature, it thermodynamically one can say that one can have a higher efficiency. But apart from that also there are various other circuit parameters which contribute to that, and we have discussed in case of TEG as well as in case of TIC. Energy density is also, the TEG device is relatively low, which you talk in terms of microwatt per millimeter square. This is a typical unit of energy density being used for these devices. Okay. Maximum you can say 17,000, typically here it is higher. Okay. So, these are the difference between TEG and TICs. So, it seems that TIC has lot of promise, and then that is a reason why people have again looked into this TIC, and I told you in the last class what is the motivation of starting again research on TIC material and the generator itself. Okay. Now, let us look at material aspect. So, what are the materials for thermoionic conversion? Okay. So, there are, we can say there are actually two material, one is emitter material and another is collector material. These are the two components where materials are used. In between it is vacuum, so there is no material. Okay. So, let us look at the emitter material. So, what is the most important property that I told for an emitter material is an appropriate electron work function. When we say that appropriate electron work function is that when we optimize the work function, it should be in such a way that the work function is relatively low. Okay. And how did we define work function? Work function is basically the energy required to take one electron from Fermi level to the vacuum level. all right. Along with other properties, work function should be relatively low, so that we can have a efficient thermoionic process. Okay. High melting point. This is a very important property, because if we do not find a material which can sustain at a higher temperature, then one cannot have a efficient the electron emission from the emitter. Okay. So, therefore, when we choose a material for the emitter, we have to see that its melting point is high, so that it remains stable at higher temperature. High thermal and electrical conductivity, it is a very important point, because we are heating this material, a emitter material, okay, at a particular location of the material. Okay. So, heat has to be conducted throughout this emitter material, something like this. So, we provide heat energy to the emitter material, and this heat should be conducted properly in the material, so that it can eject electrons properly. Okay. And the flow of electron is also important, because these electrons, they are collected in the collector material and they are again coming back. All right. So, electrical conductivity of the material also should be high. Okay. And fourth is chemical and mechanical stability. This is a very important point, because you know that this type of the devices, thermoionic generator devices, it works in a vacuum condition. Okay. There may be some chemical change which are coming from the surrounding. It always happens, because I mean at a certain lower pressure also there are some gases which are always present. All right. So, if it is chemically very much reactive and it loses its stability, then there is a problem. It will impact the emission probability, and therefore, it should be chemically stable and mechanically stable. Mechanically stable in the sense that we are talking about at very high temperature phenomena. Okay. And if at very high temperature, if there is a mechanical instability of the material, there is a problem, because we will having a brittle material or something that will eventually it will not be able to emit properly, okay, or it will not be able to sustain its own property if it does not have enough mechanical stability. So, when we search for a material for emitter, we have to see that all these conditions are met. Now, we classify different materials which are being studied in the as emitter material of a thermionic converter. Okay. So, one of the most important class of material which are routinely used in thermionic converter are refractory metals. So, what are refractory metals? Refractory metals are the tungsten, molybdenum, tantalum, etc., niobium, etc. So, these are the metals, refractory metals which are routinely used in thermionic generator, because they have certain advantages for using. What are the advantages? They have high melting point, which I just now I discussed. What is the requirement of high melting point for a emitter material? They have good electron emission. They have relatively lower work function, although not very low work function, but relatively lower work function, and I will show you the table and show you how these different materials emitter materials the work function values are. So, you will see that refractory metals typically their work function range is say 4 to 5 electron volt. Okay. They have very good chemical stability that is required. This is what I told you. Okay. Strength and creep resistance, that means they work in the high temperature environment and therefore, the stability should be very good for the material. Okay. They should be stable with high mechanical strength, so that they can withstand this environment properly without any damage of the material. All right, and they have thermal conductivity. So, sometimes these refractory metals are also coated with something in order to reduce the work function, like thoriated tungsten. Tungsten is a very popular refractory metal for this thermionic generator, but its work function relatively high. But if you make it thoriated, you just coat it with thoria, then the work function can come down, okay, and you can use it as an emitter material. But there are certain challenges. The challenges are with brittleness. At certain temperature they become brittle. Okay. They have the problem of oxidation, because I told you this chemical stability is very important. Although we work at a vacuum environment, but still it is very difficult to get rid of the oxidation, because when we use the terrestrial source, okay, it is very difficult to get rid of the oxidation, and therefore, one is to be very much careful that it is chemically it remains same. So, oxidation is a challenge. Interdiffusion, this happens particularly when they take temperature from say nuclear reactor, there is a diffusion, interdiffusion to the fuel element of the nuclear reactor, and there it creates a problem. And work function, as I told you, the work function of the refractory metal is not very low, they are moderate, but not very low as some other materials which we will discuss. The second set of material which people have used, okay, are oxide coated materials or oxide materials. Okay. Some of the popular oxide materials are barium oxide, strontium oxide, calcium oxide, or combination of different oxide. This is what people have shown, that they are having very low work function, and there are some oxide mixture which can be very efficient emitter. There are some metals which are used as base metal for oxide, and nickel is a very good base metal. Okay. So, you use a base metal and make a coating, and nickel one can use it a base metal, and then operating temperature. Their operating temperature range is also higher. Okay. So, these are some advantages of oxide material, but they have some limitation, like oxide coating can be fragile, okay, and they are susceptible to mechanical shock, to damage from mechanical shock or high energy particle bombardment. It happens sometimes if we use these devices in an environment where there are high energy particle bombardment, then there is an issue. Now, let me tell you work function of some typical material. So, if you look at molybdenum, it is 4.15 electron volt, not very low. Similarly, nickel, so tantalum, tungsten is again 4.54 electron volt, which is a popular material. Okay. Some material like barium has lower work function, cesium has slightly lower work function, iridium is again high work function, platinum is higher work function, rhenium is higher work function close to 5 electron volt, thorium is slightly less 3.38 electron volt, But now when we, as I told you, when we combine the material like barium on tungsten, the work function reduces to 1.56 electron volt. Okay. So, this is the the making the two material or combining or making a mixture of material to reduce the work function. From cesium on tungsten, the work function is reduced to 1.36 electron volt. Thorium on tungsten, which is a popular one, it reduces to 2.63 electron volt, and thoria is 2.54 electron volt. And now one typical oxide material which is very popular, it is combination of two oxide, say barium oxide and strontium oxide, the work function is quite low. Okay. So, the combination of oxide is another very good choice of a thermoelectric emitter material. Apart from refractory metal and oxide, there is another class of material which is very popular for thermoelectric converter. Okay. So, these materials are hexaborides with lower work function. Some of the popular materials are lanthanum hexaboride, okay, cerium hexaboride, etc. So, they have relatively low work function, the melting point is very high, much higher melting point as compared to oxides. Okay. They are another very important property is they have very good chemical stability, they have very good crystalline structure. So, they are mechanically strong, and I have already told you about their very high chemical stability. So, these are the class of material, particularly lanthanum hexaboride, which you will see commercially in many electron emission devices now people use. Okay. So, I told you about various material for electron emission, okay, and their properties and the advantages and some disadvantages of this material. Now, let us come to one point which I mentioned in the previous class, that is negative electron affinity. Okay. So, how did we define the negative electron affinity? Negative electron affinity is the energy required to take an electron from conduction band to vacuum level. This is the electron affinity. Okay. So, this we can write this energy difference between the vacuum and the but as I mentioned in the previous class, if the vacuum energy level becomes lower than the in some cases, okay, then the conduction band energy, then it becomes a negative electron affinity surface. So, once this you can make the surface as negative electron affinity surface, it has become a potential electron emitter. Okay. And diamond is a material, diamond, boron nitride, aluminum nitride, these are the materials which are which shows this negative electron property, electron affinity property very regularly, and then they have a better electron emission probability. Okay. So, we know that in diamond is nothing but the carbon atoms which are hybridized in a typical hybridization sp3. If you might have studied about the hybridization, different hybridization of carbon in different different allotrope, like in graphite it is sp2, carbon it is sp3. Okay. If you look at the current density of diamond after doping with certain, say nitrogen, nitrogen can make a very good donor level in the carbon, okay, or in the diamond, and that gives more electron. If we look at the current density at various temperature, it is not very high. Okay. We can only see very small current, or the emission current is of the order of nanoampere. But as soon as you shine it with hydrogen plasma, or you put this material in hydrogen plasma, you see that hydrogen gets attached to different, the bonds which are dangled to the surface, or the free bonds. Okay. Only at the top surface hydrogen goes and sit inside. It creates a negative electron affinity, or NEA surface. And as soon as the negative electron affinity surface is formed on diamond, you can see there is a huge rise in the current density, almost 10 to the power 3 times higher current density, emission current. Okay. So, let us look at again this energy diagram in order to understand that what energies are there when we have a diamond and we have a hydrogen terminated diamond, or when we incorporate hydrogen in the diamond. Okay. So, look at this, the top one. So, this is conduction band minima and this is valence band maxima. This carbon 1s level. Okay. So, let us look at this energy scale. All right. This is the vacuum energy. Look at this is vacuum energy. Okay. And this is EC, that means conduction band energy. So, how do we define the electron affinity? We define it, this vacuum energy minus electron affinity. So, chi and this value is for diamond is positive. All right. And how do we define the work function? Let us look at the work function. This is the energy required to take electron from Fermi level to the vacuum level, and this value is 4.97 electron volt. Okay. And then one can define a quantity, the difference between the valence band energy to the Fermi level, which is 0.88 electron volt. Okay. And this is binding energy, anyway we are not dealing with this. Okay. So, the main point here is that the carbon or diamond, the electron affinity is positive and its value is around 0.38 electron volt. Now, we put hydrogen. So, as I mentioned that experimentally that it has been shown that as soon as it is exposed to hydrogen plasma, okay, it becomes a negative electron affinity surface. Okay. So, now you can see that this is now the vacuum level which was there, sorry, this is the conduction band level now, you see, and this is the vacuum level, and now the chi value becomes negative, which is minus 1.27 electron volt. So, this is a very important thing. Okay. And when we have this situation, then effectively the work function is reduced. All right. So, the electron emission probability enhances. Electron emission enhances because of negative electron affinity, which modifies these energies. Okay. And this is a very important process by which one can have a better electron emitter. Okay. So, it is important to understand this, and whenever one actually wants to work in any electron emission process, it is always better to look at the surface or make the surface of that emitter in such a way that one can get a condition of an EA or negative electron affinity. Okay, so I had discussed about all about emitter material, different emitter materials. Although lot of works are going on these days on this emitter material, and one can survey these various other emitter material also. So, let us just look at what are the collector material generally used and what are the property of the collector material. This is another the material which is used in the thermoelectric generator. So, it should also have good thermal conductivity, okay, because the again this the electron which goes through this or collected in the collector, okay, if there is a good path of thermal conductivity, as it is used in the high temperature environment, it will be always efficiently work for the generator or for the device, and it should have also that high electrical conductivity, so that electron can pass through the collector. Low work function, we have seen in our previous lecture, this output voltage is actually proportional to phi emitter, phi collector. So, we have to always choose a material where the work function of the collector is less as compared to the work function of the emitter. Here we need an optimization because we want a lower work function of the emitter also, and now if we need a collector which is work function which is further lower, then we need to look at all the aspects of the device, okay. But it should have definitely a lower work function, and surface properties is very important, because you know what is happening in the collector. It is collecting the electrons, okay. So, the surface of this collector should be such that it can efficiently collect the electron or accept the electrons, okay. So, one is to look at the surface properties and resistance to sputtering. Sputtering I already mentioned that it is actually the removal of the material species by bombardment of something. Here also it is continuously getting bombarded with electron, okay. All right. So, and also if we use it in an environment where there are energetic radiation environment, which are basically used as a probe for sputtering of a material, the sputtering probability should be low, so that it does not damage the surface. Sputtering is a surface phenomena, and surface should not be damaged by the charged particle which the collector is facing, okay. So, what are the common collector materials? Again, the refractory metals are used as collector. You have to choose the proper refractory metal. One can have one metal as emitter, another metal collector, and then one is to see that what are the work function difference. And then again different metal oxides are used, some composite materials are used for collector, okay. So, I discussed about the materials of a thermoionic generator in terms of its emitter and collector. Now, before we close this discussion, we have to understand a very important process. You see that we make a thermoionic generator or thermoionic converter by giving lot of heat energy to the emitter. That means we have to raise the temperature of the emitter. Now, if you remember, initially I discussed that there are processes like field emission, which is an electron emission by quantum mechanical tunneling process, and there is no heat or thermal energy is supplied to this field emission of electron process. So, therefore, one phenomena, that is thermionic emission of electron, which works at a very high temperature, and there is another phenomena, that is field emission of electron, where you do not need to give any heat energy or do not need to increase the temperature, only you apply an electric field between cathode and anode, okay, and then by quantum mechanical tunneling process the electron comes out. So, we can just think about this situation, say that this is the material with say Fermi level E f, this is the vacuum level, E vacuum, okay, and then this is the work function phi. So, we define work function of any material in this way. Okay. So, now I consider that electron, this is a picture which I have given initially also, this is the Fermi level. Okay. This is a vacuum level, all right, and this is the work function phi. Now, can I reduce this work function? Okay, so what I told you that this is the cathode or emitter and this is anode or collector, and if we apply a bias, okay, across this, what will happen? This barrier which these electrons which are there up to Fermi level, they see an infinite kind of barrier, or they are not able to cross the work function. So, the main barrier in front of them is work function, and this barrier height is this much, this is the barrier height. Okay. So, if we can lower this barrier height, make some situation like this, if we can lower this barrier height, then is it possible that these electrons which are there at the Fermi level, this is the Fermi level, can be emitted. So, what happened when we apply an electric field? There is an electric field here which can reduce. So, this is actually the potential. So, you can consider this is the potential energy, say along that direction. So, you can reduce this by you can reduce this by this electric field. Okay. This is not actually the subscript, it is the Z value or the potential. All right. And then further a reduction can be done, because whenever there are charges, say if I consider this as a potential line and I have electron in one side, then there is a formation of image or image potential, which we know in the electrostatics, that is typically a Coulomb potential, image potential. So, I can write V image, which is proportional to E square by Z. Okay. This also actually reduces this work function phi. All right. So, eventually what happens, the electrons are, because now it is having much lower barrier, energy barrier in front of it. So, it can quantum mechanically tunnel out from the Fermi level to the free state. Okay. That means from cathode to anode. So, we already had say electrons due to thermionic emission, and now we have these red electrons which are due to field emission. It is a very interesting process which we call field enhanced thermionic emission, and this is what these days people are looking for. Okay. So, what you do, essentially you make the same cathode anode environment, give a temperature to the cathode, and you allow this electron emission process. Okay. Apart from that, you also apply a field, electric field. So, what are the key parameters? One is the work function. So, we have seen how work function is modified when you make a field assisted process, and there are two important parameters now you play with. One is electric field and temperature. Temperature was always there because it was thermionic emission process. Electric field is now added there, and we have an enhanced process or an additional process which is enhancing the electron emission. Okay. And that actually increases the overall efficiency of the thermionic generator, okay, or the device, because it lowers the operating temperature. And now you have a field assisted emission also. All right. So, it lowers the operating temperature, it increases the emission current, because now you have electrons which are emitted by this field emission process also. So, overall the emission current enhances, and overall it improves the device performance. Okay. So, now the question is, when we want to make an emitter where we would also like to have field emission process, how do we design this emitter? So, it is always better that we design this emitter which has a very good aspect ratio. Aspect ratio in that sense, particularly when we talk about nanomaterial. Okay. Aspect ratio is in that sense that this height of this emitter should be high and the radius of this emitter should be low. Okay. So, I can write an aspect ratio. So, aspect ratio can be increased if we increase the height of the emitters and the radius of the emitter. So, typically nanotube or nanowires are the choice, okay? Nanotube or vertically aligned nanowires. Now, on top of it, if you coat it with a low work function material, that actually enhances the electron emission probability to manifold. Okay. So, when we would like to add this field assisted electron emission process, thermionic process, we have to design the material in such a way that it is vertically aligned with very good aspect ratio, as well as it is coated with low work function and overall increasing the emission probability. All right. So, let me just mention few important application of TIC. So, it is used in waste heat recovery, powering spacecraft, in the nuclear reactors, there are automotive applications, there are terrestrial application, there are domestic use, high temperature sensor, etc. So, there are a lot of application of thermoelectric thermionic thermionic converter or thermionic generator, and some of them I will discuss in the next class, okay, explaining that how this application is important or the thermionic converter is important in this type of devices or equipment. Okay. So, let me just summarize the what we have discussed about thermionic converter or thermionic generator. So, we had started with certain historical perspective of this phenomena, okay, or electron emission phenomena. Then we have seen what are different electron emission process, okay, that is thermionic process, field emission, photo assisted electron emission, secondary electron emission, and then we discussed about basics of thermionic emission. Okay, what are the basic equation like Richardson equation that actually control the thermionic emission process, and then we have seen when we want to make a thermionic generator, what are the steps one follow in order to get a thermionic energy generation, okay, or make a thermionic energy generator. Then we have also seen what are the emitter requirements, all right. We have seen what are the properties of the material that gives a very good thermionic emitter, and then today we discussed what are the components of a thermionic converter. Okay. Then we have seen what is the typical device configuration considering all the heat processes or heat energies involved in a thermionic converter, where we have seen the Q in is the input heat and Q out is the output heat. One is from the emitter, another is through the collector, and then other components of heat which are contributing to this thermionic generator. Then we made a brief comparison between thermoelectric generator and thermionic converter, okay. And then we discussed broadly the material aspects. So, in the material aspects we have seen that the classification of materials are for the emitter material and the collector material, and we discussed in detail different emitter material like refractory metal, oxide, and the hexaborides as good thermionic emitter material, and what are the key properties of this material. Those are essential for a good thermionic emitter. We also have seen certain disadvantages of some material, and that needs to to be overcome by the research and the different material design. And then finally, we have seen the field assisted thermionic conversion and its advantages. Then along with the temperature, if we also apply an electric field, then we can have a better or enhanced electron emission, and then we can lower the temperature with higher electron emission, that means with higher efficiency, and this is the future direction of research of a electron emission device. Thank you.